Okay, so this is the second talk of the series, and in the first talk I talked about Landau level spectroscopy, and I showed you how we can basically tell by looking at the Landau level spectra whether we have massive or massless Dirac fermions in any system. We can, there are many more things we can do with Landau level spectroscopy. We can actually get G factors very easily. If there's a G factor that's different from 2, then we can measure that. I was going to show you something on electron-phonon coupling, but there wasn't enough time. But if you're interested, I'm happy to talk about that later. So Landau level spectroscopy is a very powerful tool to measure many of the electronic properties of a system. The other equally powerful tool is quasiparticle interference Fourier transform spectroscopy. So today I'm going to be talking about how we use this other tool to explore the electronic properties of Dirac systems. And especially, I'm going to be talking about inhomogeneous systems. So everything I spoke about in the last lecture was homogeneous systems. Today I'm going to be talking about two kinds of inhomogeneous systems. One is a one-dimensional inhomogeneous system, which is a one-dimensional oscillation, and the second is a two-dimensional checkerboard pattern. And I'm going to be talking about how these one-dimensional and two-dimensional superstructures can affect the properties of Dirac materials. So let's first start with the striped topological insulators. Why are stripes interesting in a bigger picture context? One of the reasons stripes might be interesting is you've heard many talks about trying to first realize edge modes and then measure edge modes.
Sorry, there's a lot of noise on your recording mic. Can you?
It's here. So.
Okay, outside of I can check. Okay, yeah.
Is that better? Okay. Okay, sorry. So why would you want to look at striped systems? One reason is edge modes, okay? So as you know, one way to achieve an edge mode is, is to have a structure like this where you have a three-dimensional topological insulator and you put two strips of different magnetization on the top, and you expect to get a chiral edge mode in between these two. But there's another simple way to achieve an edge mode, which is, what if you could have a potential variation in a system where you had the potential oscillating as a function of real space, and then if you were to turn on a magnetic field, and of course if you were to be able to position the Fermi energy at the right position, then also you will find a chiral edge mode at the boundary between these potential variation regions, okay? So this is one reason why you would be interested in studying these kinds of striped topological insulators. Okay, so the material I'm going to be telling you about is bismuth telluride. It's one of the quintessential 3D topological insulators. It's got a layered structure. Can you see the pointer? There it is. Okay, so I'll show you later. We cleave and we expose the tellurium plane. And so what you expect to see, it's got this hexagonal arrangement of atoms, and that's what we should see on the top surface. The calculated band structure for this material looks like this. I'm having some trouble with the pointer. Okay. So pretend I have a pointer. So the calculated band structure looks like this. You can see the conduction band, the valence band, and the line in red represents the surface state. Notice that the surface state, the Dirac point is very close to the valence band edge. Okay, that's one thing to notice. So you can't really see the other side of the Dirac point. In addition, this calculation has been done for two high symmetry directions. So along one high symmetry direction in the Brillouin zone, it looks like a Dirac cone, but along the other direction, there's some warping. right? There's a distortion. So the constant energy contours of the system start off looking circular, and then as time goes on, as you increase the energy, you can get, they look hexagonal and then snowflake-like and so on. Here's ARPES studies on these materials. You have some beautiful ARPES data. And they can clearly see along this gamma k direction, you see the Dirac cone, and along gamma m, you see the warping of the surface state. Okay, so we cleave the material to do STM, expose the tellurium surface, and that's what the surface looks like. And you instantly notice you have all of these beautiful patterns, and each of these big structures is a single impurity defect. And there are many different kinds of single impurity defects. There's this one that looks like this, there's this one. The other complication in this material is because it's a semiconductor and the density of states is low, we can actually see many layers inside the material. So some of these impurities are actually coming from other layers, not just the surface layer. If you zoom in, you can see the hexagonal arrangement of the atoms. I don't know if you can see it clearly, but here's the triangle. So you can see the hexagonal arrangement of the atoms, the tellurium atoms. Many times when we take large areas topographies, it looks flat like this. But quite often, the topography looks like this. And if you take an even larger area, this is 3,000 angstroms, then you can see stripes in this material. So the question is, what are these stripes? And how do they affect the density, electronic structure? Yes?
What are your defects? Do you have some substitutional defects?
Yes. Yeah, absolutely. We have all kinds of defects. We have substitutional defects. So this is the tellurium plane. So tellurium atoms substituted by bismuth atoms. Then we have tellurium vacancies. So those are two primary defects on the top layer. But then there are other kinds of defects in the subsequent layers that we also see.
And you can know which defect it is? Just by scanning?
There are people who can tell you which defect it is. I can't. We haven't really done any analysis of which defect is what, but I think you could do something systematic and figure out the identity. We've tried, but it's sort of tricky. It's not easy. Okay, so if you take a line cut to through the topography, you can see that these variations in height are just about an angstrom. Okay, so this is not a huge topographic, stripe. It's just about an angstrom variation in height from the crest to the trough. In these striped areas, the crystals, the surface structure looks pretty nice. If you go to any spot and you zoom in, you still see a nice arrangement of hexagonal atoms. So nothing else has been disturbed. So the first question you ask when you see something in STM, is it electronic or is it actually a buckling? Okay, that's the first question. And we did a lot of different tests to rule out an electronic stripe. And one of the most convincing things is we did SEM and we saw ripples even in the SEM images. So we were pretty convinced, based on all our data, that these are actually physical stripes, meaning that the height of the surface is actually changing as a function of position. So the question is, what is the effect of this buckling on the electronic structure? So first, let's use our tried and true technique of Landau level spectroscopy, turn on a magnetic field and look at the Landau levels. And let me just remind you, what you expect to see is states at different energies labeled by this integer n. And you also expect to see one non-dispersing state at the Dirac point. And I also want to remind you that semi-classically speaking, the area occupied in K space by each level is just pi K squared, which means that, and K therefore is proportional to square root of NB, which means that if you were to measure the energy of any Landau level, which we can because we know the position in energy of the peaks, and you know the index of the Landau level, and B is a magnetic field that we apply, so we know that. So that means that if you know E you know K, and you can plot the dispersion. Okay? Now this dispersion is not going to be continuous, you'll get a set of discrete points, but still it is dispersion. Okay, so here's a spectrum with the magnetic field turned on. The U-shaped background is actually just what it looks like in zero field. And here's the same spectrum with this background subtracted. And now you clearly see the Landau levels. We can identify these by integers as n equals 0, 1, 2 based on their field dependence, okay? And I'm not showing you that. So here's energy of each peak versus square root NB, and it's a beautiful straight line for this surface, okay? So this is a Dirac system. All right, now let's ask what happens on the striped region to the Landau levels. And let me tell you, what I'm going to show you next is actually unexpected. Let me just tell you, in case you were wondering whether you should pay attention or not. So let's do the following. This is the Dirac point. This is the first Landau level. Here's a striped region. Let's actually take a dI/dV map in the magnetic field in the striped region. And then at each point, identify the energy of this peak and plot it as a function of position. And if you do that, that's what it looks like, okay? So this means, the scale, and it's missing, the scale is missing here, but basically, depending upon whether you're in the dark region, which is the trough, or the bright region, the energy of the Landau level peak is different. You can see that by taking a line cut. So here's the topography, here are the stripes. You take a line cut through this region. This is the variation in the topography. And this is the variation in the Landau level energy. So the Landau level energy mimics the topography. This is not that surprising. You might expect this if you had a potential variation, okay? But what is surprising is this. Now let's take the same line cut and plot all the Landau levels. So here's the first Landau level. It varies as the topography does. Here's the second one, it varies less, and so on. By the time you get to the fifth Landau level, all the variation is gone. That means the Landau level energy doesn't change as a function of position. Okay, and you can see this better here. Here's a spectrum in the dark region and a bright region, right? Bright region is red, dark region. So you can see the peak positions are offset, and then they get homogeneous. So now if I were to plot what I would call the dispersion, it looks like in the dark regions, that is the troughs of the stripes, the dispersion is no longer linear. And then you might say, hey, wait a second, the only way this can happen is if you develop a mass, but there is no time reversal. These impurities don't break time reversal symmetry. The stripes don't break time reversal symmetry. There's no reason to expect a mass in this system. So the question is, what is this due to? One possible explanation, actually there are two possible explanations. One is that the zero field dispersion is different, right? The other explanation for what we're observing is that the zero field dispersion is not what is causing this. The Landau levels are affected by something other than just the zero field dispersion. Okay, so let's look at the spectrum at higher energies, and what we find is actually there's this little bump in the spectrum that tells us the position of the valence and conduction bands, actually the conduction bands. It looks like the conduction bands are shifting by the same amount as the first Landau level and the 0th Landau level. So it looks like the stripes create some kind of potential variation such that the entire band goes up and down with the stripes. If that's the case, the first question is that also shifting the surface states in the same way? And if it is shifting the surface states in the same way, how do you explain the Landau level behavior where only the lowest Landau levels are shifted and the higher Landau levels remain homogeneous? Okay? So in order to answer this question, we did quasi-particle interference Fourier transform spectroscopy. The name sounds very complicated, but actually the technique is very, very simple and intuitive. Just to remind you, the dI/dV is proportional to the square of the wave function So this allows us to measure interference, okay? So if you have some kind of a two-dimensional electron gas on the surface, and if you have a scattering center, the electron waves get scattered by the scattering center, and where they overlap, you get an interference pattern. The wavelength of the interference pattern is 1 divided by the difference between the initial and the final momenta of the two states. Okay, that's the wavelength. So if you could measure the wavelength, you would be able to actually measure this difference, and you know the energy because you set the bias voltage, and this is one way to get dispersion. Okay? So in 1D, this is very simple to see. So let's just take an example of a free electron traveling in one dimension whose wave function looks like this. If you were to square this wave function, you get a constant, and there's no contrast. But then if you have scattering process where you have an incoming wave and a reflected wave, the resultant wave function looks like this. Now if you square it, you get a wave with a frequency that's, with a wavelength that's given by 1 over 2k, where 2k is the difference between the incoming wave and the outgoing wave. Okay? So if you have scattering processes, then you can get waves in your system. And in general, in 2 dimensions, psi squared for a free electron would just be cosine of the difference between the incoming and the outgoing waves. So this is a very powerful thing. We can actually get a lot of information by looking at these interference patterns. Just to give you an example, here's a dI/dV map taken on copper. Copper has a 2-dimensional surface state with parabolic dispersion. Now this is ARPAS data. At some energy, it's a beautiful circle. The constant energy contour in momentum space is a beautiful circle. If I take this dI/dV map and do a Fourier transform, I get a circle. And the diameter of the circle, the radius of the circle represents this scattering process, which is the dominating scattering process, okay? And actually, we see all the scattering processes, possible scattering processes, but this one dominates our Fourier transform. That's because it's next to a stationary point. Okay, so if we were to do this, and there's a problem, I'm going to have to. We can take dI/dV maps as a function of energy and do Fourier transforms as a function of energy. And if we were to do that, then I'm going to show you what the Fourier transform looks like as a function of energy. Going from the bottom of the band and sweeping up, you should see circles that get bigger and bigger with energy. So you see a circle coming, there it goes. Great. So now if I can plot the radius of the circle with energy, I get a parabola, and this is dispersion in copper. Yes?
Shouldn't it be a filled circle?
Very good question. Yes. In theory, you should see all the scattering processes, and it should be a filled circle. But the thing is that close to this backscattering, you have a lot of states with the same Q vector. So you have this one, we have a bunch of states with very similar Q vectors. So that signal is very strong. The second thing is the other signals actually cancel each other out. So this combination of things gives us the circle with the radius of the backscattering Q vector. So essentially in STM Fourier transforms, you measure the signal from areas of the Fermi surface where the joint density of states is very large. Okay? So if you did an autocorrelation of this, a circle for example, you would get a circle. And so typically in order to predict what we're going to measure in STM, we do an autocorrelation. And that ends up being what we see. Okay? Unless there are spin textures and so on. Okay. So that's copper. Now, the other thing I want to tell you is about the Fourier transform is that what you see in a Q space the Fourier transform space, reflects the Fermi surface contours, the topology of the Fermi surface in momentum space. So here the Fermi surface topology is a circle, so you get circles. Here, for example, in this topological crystalline insulator, the Fermi surface looks like this. You have four electron pockets at the x and y points, and the Fourier transform of the dI/dV map reflects that. Okay? So, in fact, it's a very powerful technique to actually look at Fermi surface topology. Here, for example, it's the Lifshitz transition in a topological crystalline insulator, where you go from two independent Fermi surfaces to a position where these things have merged to, to actually an electron and hole-like Fermi surface. And now you see below the Lifshitz transition, you get these four dots, and above you get circles. So the Fermi surface topology gets beautifully captured by the Fourier transforms. Okay, now let's do use this technique on bismuth telluride. Here is a topography again, and here are all the other impurities I was showing you earlier. Here's a dI/dV map, and here's the Fourier transform. And now, just by looking at this Fourier transform and remembering that this should reflect the topology of the Fermi surface, you should know that the Fermi surface has some hexagonal character to it. And in fact, as it turns out, as I told you, as you go from near the Dirac point to high energies, the Fermi surface changes from circular to hexagonal to snowflake-like. Interestingly, here when it's a circle, remember I just showed you that the dominating process that we see in STM is backscattering. Backscattering is prohibited in these systems, so as long as the Fermi surface looks like a circle, we get no signal in these systems, which is like indirect proof that backscattering is prohibited. Okay? So in these systems, we can only get information using QPI at high energies. Okay, so the dominating processes that we measure are these scattering processes, because these two pieces of the Fermi surface are actually parallel. So this scattering process gives rise to this set of Q vectors. Okay? All right. So here are a bunch of dI/dV maps at different energies. We take the Fourier transform at different energies, and you can see that its size is changing. That reflects the dispersion. And here's the Q vector that we get, and all that is great. And actually, this line here is the ARPA's, measured dispersion along two different directions, and these dots are what you get from STM. You can only get data at higher energies, okay? But it matches the ARPA's really well. Okay, now let's go to the striped region. What do we do in the striped region? Well, one thing we could do is remember there's a contrast that we're looking for between the trough of the stripe and the crest of the stripe, okay? We want to see what happens to the dispersion in these two regions. So let's just define two areas. We'll define this pink area, and then we'll define the blue area. One is the crest and the other is the trough. We'll use these as masks, and we'll take masked Fourier transforms of just the trough and the crest areas. Okay, so here's one area. This is the crest area, and this is the trough area. And here are the Fourier transforms. And actually, here's this subtracted from this. And if you look carefully, it's not very clear here, but this red line represents this, and the blue line right next to it represents this. So they're shifted. So in fact, if you compare them side by side, you can see that these Q vectors are actually smaller than these Q vectors. This is smaller than this is smaller than this, and so on. So you can actually take line cuts and plot the Q vectors, and you can see that consistently, as a function of energy, the Q vectors have shifted. So what we get from this is that at high energies, there's a parallel shift of the Q vectors between the trough and the crest of the stripe regions. At low energies, the n equals 0 and 1 Landau levels also show a similar shift of about 10 to 12 millivolts. So then what's happening at these intermediate energies? From the high energy and low energy, this looks as though the potential variation, the stripes are creating a potential variation, and all the bands shift rigidly as a function of position. Okay? So now this thing in the middle is a mystery, and it took us a long time to figure it out, actually. It took us a year from the time we got the data to the time we figured out what was going on. Now in retrospect, it seems so obvious. So these are Landau levels, and Landau levels are not localized objects, right? Landau levels are extended states, okay? So here I'm plotting the Landau level wave functions for a very simple system, right? Like this is not a Dirac system for parabolic band, but these have been plotted on top of the stripes. You can see that the square of the wave function quickly goes from being confined to a small region inside the stripe to spanning the stripe. So in the Landau gauge, right, the wave functions, the Landau level wave functions can get pretty big compared to the size of the stripes. So what this means is that when you're at the lower Landau levels, you actually, the measurement that you make is quite local. But the moment you go to the higher Landau levels, you're actually, the Landau level wave function is averaging over the entire stripe, so it actually doesn't see the effect of the stripe. So this is a real thing. The Landau level is actually not affected, the higher Landau levels are not affected by potential variations. So you can actually use perturbation theory to simulate this very easily. Just say that you can, you know the wave functions, you simulate this stripe as a sine wave, and you can actually figure out what the dI/dV should look like. And here's a simulation, and here's the data, and it actually matches the data really well. You can see from the simulation that at higher Landau levels, you begin to see some variation because the wave functions are getting bigger and bigger, and they're able to sample the next period of the stripe. So this is great. This means that we know what the stripe potential is doing, but it also means that if you were to use Landau levels to look at a spatially inhomogeneous system, or you were to design a system where you would like to use Landau levels to create discrete states, then you have to be aware that the size of your spatial features will affect how the Landau levels respond, okay? All right. So now in this system, the first Landau level changes like this. And if I were to position the Fermi energy right here, I would get, in theory, a chiral mode right at the boundary between the stripes, okay? And this would be a neat experiment to do. These stripes are long-range stripes, so you can in fact imagine doing such an experiment, but we haven't done it yet. Okay, so I'm going to go on to the next two-dimensional potential variation in a different system. If you have any questions before I do that? Go ahead.
So, just to make sure that I get it right, you're saying that this Landau levels, as you're going to higher end, they're spreading out.
Yep.
And if they're spreading out, then they're averaging over a large number of stripes.
Yeah.
If they're averaging over a large number of stripes, shouldn't the effect go away?
It does.
But you're seeing a shift at higher end and at lower end, but you're not seeing any shift in
So the higher end shift that I showed you was from quasi-particle interference. The middle shift, it does go away. We don't have Landau level data. So the Landau level...
higher end as well.
No, so the actual potential variation hasn't gone away. It's the Landau levels that don't see it. Even at these energies, the potential variation exists, but the Landau levels are oblivious to that potential variation because they're so big.
And any reason why you have these stripes?
We think we're not sure. It might be because of cooling down the sample, or maybe they happen during growth due to strain. We're not sure. Did you? Yes, sorry.
Seems like your argument is gauge dependent.
Yeah. So we use the Landau gauge because it fits the symmetry of the problem.
Okay.
If you can use the other gauge, it would make our calculation more difficult, but you would get the same answer. If you notice, we summed over position here. That's because we're using the Landau gauge. If you use the other gauge, you would sum over whatever that other quantum number is. M and L. Those are the quantum numbers. So you just sum over that and you should see the same thing. But it doesn't make sense to use the other gauge for this symmetry. Yes? Correct. We don't know what it is. It's a mystery peak. We called it a mystery peak when we wrote the paper. We still haven't figured out what it is. It's been many years. We've been trying to figure it out. We don't know what it is.
What's happening with the bulk bands or whatever they're shifting?
So if there's a potential variation, it's a very simple potential variation. Everything shifts rigidly. It's not a correlated electron system where you can imagine different pieces shifting differently. The whole band structure moves up and down with the potential.
So you were measuring the conduction band and Mills band on the surface, like exactly at those.
Yeah, exactly at those points. Everything moves. Yeah. So we see from our spectra that even the spectra are shifted with its position.
Remember, I think those states are spread out, so why are we seeing by the same logic, I'm thinking that all states will be spread out.
Yeah, but the wave functions, you're right. But the wavelength of those states is quite small, actually. Yeah, it's not as big as 1,000 angstroms. Yeah. Any other questions? Okay. So if there are no, how much time do I have?
25 minutes.
Okay, this is perfect. Okay, in the next 25 minutes, I'm going to be talking not about 3D topological insulators, but about topological crystalline insulators, where strain can have a big effect on the Dirac nodes. Okay, and the reason for this is in TIs, the Dirac node is at the time reversal invariant point. And unlike graphene, you don't expect to see pseudomagnetic fields in TIs because the Dirac node is pinned to the time reversal invariant point. Here in TCIs, the Dirac node is not pinned to any momentum space position. So in fact, if you have strain, this is a prediction, if you have strain in the system, the position of the Dirac node can change in momentum space. And this is exactly analogous to having a vector potential in the system, and therefore, in TCIs, strain can create pseudomagnetic fields. Okay? So we haven't measured pseudomagnetic fields, but we have measured, and I'll show you how we did it, we have measured the change in momentum space position of the Dirac nodes due to strain. Okay, oops, I'm going in the wrong direction, I think. Okay. So strain is a very interesting knob in condensed matter systems. Let me just give you a few examples of what strain can do. In strontium ruthenate, for example, this was done by Andy McKinsey's group, you can use strain to enhance the superconducting transition temperature. Okay? You can enhance ferroelectricity. You can get pseudomagnetic fields in graphene, huge pseudomagnetic fields due to strain. So strain is a very, very interesting control knob. We would like to use strain, measure the effects of strain on topological crystalline insulators, right? And I showed you why they're interesting yesterday. They're similar to TIs in the sense that bulk bands are inverted due to strong spin-orbit coupling. And due to this band inversion, symmetry-protected surface states emerge. But they're different from TIs in the sense that it's mirror symmetry that's protecting the Dirac nodes. And you can get an even number of Dirac cones within the Brillouin zone. Moreover, the orbital character of these states is very important for the topological crystalline insulators. Okay, so, yep.
So when you say pseudomagnetic field, do you mean it couples to the opto part or to the Zeeman part?
So I'll show you in a second what it's going to do. But essentially, I mean that if there's something in the Hamiltonian that looks like P minus P prime, right? That looks exactly like a vector potential. And therefore, there'll be a corresponding magnetic field associated with it. As long as the curl, so to get the curl of A being non-zero, you need an inhomogeneous strain. So as long as whatever you're getting is inhomogeneous, you'll get a magnetic field. Let me show you. So what are the theoretical predictions? You can shift the Dirac nodes in momentum space. You can actually create a transition from a topological phase to a trivial phase using strain, which is pretty neat. It's like a switch. You can have, there's a prediction that if you have large enough strain and you get these pseudomagnetic fields, the lowest Landau level is like a flat band. And due to this flat band, you could get superconductivity if you were to position the Fermi energy inside the flat band. And you can get, and I already mentioned the topological to trivial crossover. So let me just explain what you were talking about. You were asking me the question of what you mean by pseudomagnetic fields. So if you have strain in the system, the prediction is that depending upon the kind of strain, the Dirac nodes can shift in momentum space. So here, for example, is compressive strain. All the Dirac nodes shift inwards. This is uniaxial strain. These are all predictions theory. A pair shift outwards and two shift inwards. And this is shear strain where they shift sideways. So no matter how the Dirac points change, you can write the momentum space positions as the original position plus some shift. And that looks exactly like having a vector potential in the system. And as long as curl of A is not zero, you can get an effective pseudo-magnetic field. Is it clear? Okay. All right, so what is the system that we'd like to study? What we're interested in doing is creating a spatially varying strain. And there's actually a beautiful system that does that. And this is this thin film of lead telluride on lead selenide. Okay, they've shown that when you grow this, you get this checkerboard pattern. Okay, and this checkerboard pattern is naturally strained. And so we could go from position to position and measure the effect of strain on the Dirac electrons. But this particular material is actually trivial. It's not topological. So we wanted to study a topological system, so we decided to grow lead tin selenide, tin telluride, which is topological, on these substrates. So we used lead tin selenide as our substrate, and on top of that, we grew tin telluride, which is topological. And the recipe is very easy. It's very easy to grow these thin films. So what do you expect? So here's the lead tin selenide substrate. You cleave it, you expose a beautiful surface, and then you deposit the tin telluride atoms. And as they're falling, the first layer is extremely strained because it wants to match this lattice constant. The lattice mismatch is about 3%, okay? But as more atoms fall, you create these dislocations, and these dislocations are created to relieve the strain. Okay? And as more and more layers are formed, you have a denser and denser network of dislocations in the system. And finally, at about 30 or 40 layers, the strain is completely relieved by this network of dislocations. Okay? So we actually studied a material at that limit where DC strain no longer exists. Okay? But we have AC strain in the system, meaning as a function of position, there is strain built into the system. Okay, so here's one monolayer, no dislocations. This is highly strained. Here's 2 to 3 monolayers. You see these dislocations. 20 monolayers, a huge number of dislocations. By 40 monolayers, the surface looks like this, and then you stop getting any further dislocations, all the DC strain is gone. Okay? All right, so now let's look at the sample. That's what it looks like. These little dots are actually atoms. And in fact, if you zoom in, into the troughs, you can see the beautiful square atomic arrangements. The peaks, same square atomic arrangements. So, this crystal structure is quite good. So how do we determine, the first thing we need to do two things to look at the effect of strain. The first thing is we need to determine the strain as a function of position, and then we need to find the effect of strain. So how do you determine the effect of strain? Well, we have a really nice technique. We can actually use an algorithm to figure out the shift in the position of a particular atom from what is expected to be its perfect position. So let's say you have a perfect lattice. You construct a perfect lattice, and then you ask the question, how much has each atom shifted with respect to this perfect lattice? We can actually measure that shift atom by atom using this algorithm. And so that's what we do. This is an example of what we can do. Here's a lattice. We actually superimpose compressive and tensile strain deliberately, and using this algorithm, we were able to backtrack the strain. Okay, now let's use this algorithm to find the strain map. And here's the strain map. This is basically a map of the compressive and tensile strain in this system. And you can see if you were to average over the entire sample, there's no net strain. But as a function of position, here you have, compressive strain in the blue regions and tensile strain in the red regions. Okay. Now we want to do Fourier transform and figure out the effect of strain. Okay, so here's a dI/dV map of the whole surface, and if you zoom in, you can see it has some patterns. So you can take a Fourier transform and figure out what the Q vectors are. Before we do that, let me just show you what you expect. So here's the Brillouin zone. Here are the constant energy contours. And like I told you before, you can actually sort of guess what you should expect simply by taking an autocorrelation of the constant and of the Fermi surface. So this is an autocorrelation of this, and here's what our data look like. Okay, so you can see that we can capture much of the Fermi surface in our data. All right, so we can do this as a function of energy. This is the Dirac point. We're moving away from the Dirac point, okay? And we're going to just track what happens to these Q vectors. And these things get bigger and bigger as they should. And we can plot this and get the dispersion. So far, so good. Now what we need to do is do this as a function of position. And again, because we have a periodic system, it's very nice. We can create a mask and use the mask to define areas where we take Fourier transforms. So here's the mask that we make, right? We take a selective Fourier transform of just the red regions, and then another Fourier transform of just the blue regions, and we're going to compare them. And let's see what we see. So at some energy far from the Dirac point, here's a selective Fourier transform of the red region, and you can see that these vectors are, this is smaller than this is smaller than this. So you can see there's a Q space shift in these things, okay? You can see that in the line cuts as well. And this occurs consistently as a function of energy, and if you were to plot Q in these two regions as a function of energy, you get these two lines. Okay, now here's the problem. This looks exactly like what I showed you on the stripes. So how do we know that the buckling, this two-dimensional structure, has not created a two-dimensional potential variation that's simply shifting the Dirac, the whole band structure up and down as a function of position?
Excuse me, is this strain increase the mirror symmetries? Because this is the TCI.
Yeah. Yeah, so compressive and tensile strain do.
Yes, because it's
Yeah, so for the moment I'm just talking about those. And then I'll be talking about uniaxial strain in a bit, and that also does. Yeah. But yes, you're right, that's a good question. But remember, we're not really looking close to the Dirac point. So you can say, okay, fine, maybe it breaks mirror symmetry, certain kinds of strain, but we're not looking close to the Dirac point to see the mass gap. We're looking quite far.
But we still want to see the shift of these.
We want to see but we're seeing them indirectly through the higher energy dispersion. We don't want to go close to the Dirac point. We can't. We can't get dispersion close to the Dirac point for a different reason than the TIs, but we can't. So we are stuck to being far away. Okay, so here are the two scenarios. There's a relative momentum space shift of the Dirac nodes, which actually is very cool because if this is large enough, this can give you pseudomagnetic fields and flat bands and, you know, topological superconductivity and so on. Or there's just an energy shift, which is a potential energy shift, which is interesting, but, you know, not as interesting as this. So we can actually tell that there's no potential energy shift. In the other, remember in the TIs I showed you, there was a feature, you could track the band structure shift in energy just by looking at features in the DIDV. Here's DIDV in two regions, and you can see that the two spectra are identical in the sense that this dip position is the same, this position. So look at this axis, it's 100, this is 100 millivolts, this is 50 millivolts. To actually get this would be a shift of about 30 to 50 millivolts in energy. So you should clearly see one of these spectra shifted along the x-axis with respect to the other if there were a potential variation. So this is not a simple potential variation in the system. Okay? So basically, we would conclude, just based on all this analysis, is that we're seeing some kind of momentum space shift of the Dirac nodes due to tensile and compressive strain in opposite directions. But we can do better than this. Okay? And here's how we can do better. In the next few minutes, I'll show you how we can do better. Remember, strain is a tensor. You don't have just compressive strain or tensile strain. You have uniaxial strain, you have shear strain, and so on and so forth. You can compute all this by computing the strain tensor. And we have all the information we need to actually go point by point. And at each point, we can compute the strain tensor. And if you do know all the strain components, then you can get a much better idea of all these individual alpha, beta, and gamma, which tells you how the Dirac cones shift as a result of compressive strain, tensile strain, uniaxial strain, shear strain, and so on. So that's what we'd like to do. So what we did was we computed the strain tensor because we know all the atomic shifts. So we took this area and we computed the strain tensor. This, for example, is one of the elements uxx of the strain tensor. This is another element uyy of the strain tensor. This is the off-diagonal component of the strain tensor, and so on. And using that, we can look at compressive and tensile strain, and we get our original picture back. But now we can look at uniaxial strain, and there's actually substantial uniaxial strain in this system. Okay? So now we can go and ask the question, wow, by the way, shear strain is very small. Okay? So we're going to ignore shear strain. We can say, okay, now let's see what the effect of uniaxial strain is. And let me just show you how these actually exist together. So this is a region of isotropic compression. This is a region of isotropic stretching. And here is the uniaxial, pure uniaxial strain region, these two. Okay, so we have all of these happening in the same system.
So this strain calculation is, observation is just based on the topography?
Yes, purely, no. It's looking at shift in atomic positions. Yeah, we don't look at the slope. That would be a little tricky. Yeah, no, we actually look at the picoscale shift in the atomic distance.
You have some
Algorithm
algorithm
to calculate that. It's the same algorithm that we use for correcting drift. It's our drift correction algorithm.
How do you know what will be the positions of the atoms if you didn't have?
Yeah, that's a very good question. So let's talk afterwards. Yeah. Any other questions? Okay, so now let's look at the effect. And now what do we expect? We expect that if you have uniform compressive or tensile strain, the Dirac nodes they move together in phase. Okay, so this is a movie of what happens as we move from a region of uniform compressive strain to tensile strain and so on, and you should see that these Q vectors moving together in and out in phase. Let's see. Okay, so they move in and out in phase. I don't know if you can see this. Let's do this again. So they're in phase. Maybe you can see it here. They're all in phase. They're moving in phase. Okay. Now let's see what happens to uniaxial strain. Now I'm going to go from a region of uniaxial strain going in one direction to uniaxial strain going in the perpendicular direction. Now these Dirac cones should move out of phase. Okay? Because this is uniaxial strain, it should affect only one pair of Dirac nodes and keep the other pair unperturbed. This is slightly more difficult to see, but if you are patient, you might be able to see it. You can see they're sort of breathing. Let's try again. In this, they're moving out of phase. So when this moves out, this moves in. Okay? So this basically what this tells you immediately is that there's no potential variation that can create this kind of pattern in the Dirac node shifts where the two move in phase and two of them move together and the opposite two move in the opposite direction. So this is definitely strain. You can see that just by plotting the Q vectors. Here's Qx, it goes this way. Here's Qy, it's completely out of phase. Okay? So now we can get all of these alpha and beta constants, and this, whatever we get from our data matches theory pretty well. So all this is great. So we have seen a shift in the momentum space position of the Dirac nodes by strain. What we need to do next is to actually look for pseudomagnetic fields. We haven't seen that yet. So that's our next job. And then the next thing would be to be able to move the Fermi energy to the lowest Landau level and see if we see some correlated electron physics. That's it. Thank you for your attention.
Wait, before lunch, speaker gifts.
Oh my God. But I'm expecting a lot. I have high expectations.
You have high expectations?
Yes.
Your expectations will be met.
Okay.
Quite quickly.
Okay.
Yeah, we have time for a couple.
Oh, I'm sorry. Yeah, questions, please. Okay.
But at very long lengths.
That's, this is like you're asking the right question, but as it turns out, not over such long lengths that we would have. Over pretty short lengths here, 100 angstroms and 200 angstroms, they are completely. So, but the wavelengths of these electrons, the wave functions, the wavelengths, they're much smaller. They're actually almost enormous. So on the scale of the wavelength of the electrons, these are large.
So it's very weak pseudomagnetic.
Everything
All right. So at the boundaries, can you see something like zero lambda?
So you should be able to, we haven't seen it. You should be able.
That's very interesting.
Okay. I'm not going to use this.
Yes, please go ahead.
Do you know it's a lot of strain changes as a function of temperature?
That's a very good question. So this strain is inbuilt into the crystal, right? It might, everything is changing as a function of temperature. Band structures change quite dramatically. Atomic positions are changing. I don't know because I don't have data to tell you what happens. But it might.
What question?
Can I have that?
What? I had to give
He
the...
signed me on to it. He doesn't want to give it to me.
So, okay. So we all know that one of the most precious commodities in physics is the sleeping space on couches in the department and in labs. So we've bought for you the official Lego movie double-decker couch,
Oh my God.
so that more people can sleep in your lab.
Oh, this is really cool. Thank you so much. Like our gratitude, right?
So what would your signature be for the pseudomagnetic field? Like
Landau
how would
levels.
you actually,
Landau
but you don't see it. So
But
is it just too weak to see?
no, I suspect it's something to do